So this module, we're going to continue our discussion on hydrocarbons. That's compounds that contain only carbon and hydrogen atoms. Four broad types of hydrocarbons: alkanes, of course, that we did last week, only carbon-carbon single bonds, whether those are in chains or rings. This time alkenes, at least one carbon-carbon double bond, and so here's the generic alkene, carbon-carbon double bond. Each carbon's going to have two other things attached to it. Later on in this module, we'll touch very briefly on alkynes, substances that have a carbon-carbon triple bond, and of course if you've got a carbon-carbon triple bond, there's only one thing attached to each carbon other than the triple bond. And aromatic groups that I'll just broadly put the picture up there. We're not going to talk about those until about 3 weeks, when we will dwell on them significantly. So anyway, alkenes, carbon-carbon double bonds. As with every new type of compound we're going to look at, we'll talk about naming. Just remind you, of course, the organic way of counting, not 1, 2, 3, 4, but meth, eth, prop, bute, pent, hex, sept, oct, non, dec. Now the functional group we're looking at right now, the alkenes, that means that after we've said how many carbons there are, we then put little ene afterwards. So there's obviously no one carbon alkene analogous to methane, because one carbon cannot bond to another carbon with a double bond. So the simplest one, ethene. There's the picture of ethene. And formula of ethene, C2H4. Propene, a couple of ways to depict propene there, C3H6. Butenes, C4H8. Pentenes, NN-hexenes, heptenes, octenes, nonenes, and dekenes. And you'll notice I've been putting the plural ever since really leaving the propene, because there are tons and tons of isomers that we'll get to in a minute. They are a homologous series. If you look at all those formulas there in that last column, it doesn't take too much to see that there are twice as many hydrogens as there are carbons, so hexene, C6H12, and so on. And that goes back to what we mentioned with the cycloalkanes. We've got an extra carbon-carbon bond in here, and so there's two less hydrogen atoms to make room for that carbon-carbon bond. I promised you the isomers. So let's think about butene for now, C4H8. Now, of course, you've already encountered an isomer of C4H8, cyclobutane, 4 carbons in a nice ring with 2 hydrogens on each carbon. But we don't care about that right now. What we care about right now is the fact that it's CnH2n, is because we've lost those 2 hydrogens from an alkane, the CnH2n plus 2, because we've got an extra carbon-carbon bond. So there are various structural isomers. The first one here, where you can see that our double bond starts at the first carbon, and that will be but-1-ene or 1-butene. I will use those interchangeably when we're doing it. By the way, when it comes to multiple chains in a compound and branches and where do you start the numbering, the alkene always determines the end that you're going to start. You always start at the end of the chain closest to the carbon-carbon double bond. Now the structural isomer is where we're going to have the double bond starting at the second carbon. Okay, so that of course will be but-2-ene or 2-butene, and the formula of that CH3CH double bond CH3. Now of course that's it in terms of a 4 carbon chain with a double bond, but we can of course have a 3 carbon chain with a double bond with an extra methyl group there. So this would be a propene to methyl propene, the methyl group stuck there on the second carbon. Okay, and of course we would start the numbering up at this end. So this is carbon 1, carbon 2. No need to actually say 2-methyl prop-1-ene. There is no doubt whatsoever about where the double bond has to be. It has to be between the first carbon and the second carbon. So there we are. There are 3 structural isomers of C4H8. But there are also geometric isomers, because you cannot rotate around a carbon-carbon double bond. Thus, it's going to make a difference in the case of 2-butene or butene about whether the CH3 groups are on opposite sides of the double bond or whether they're on the same side of the double bond. And so you have these two geometric isomers. Back in my day, we called them cis and trans isomers. Cis, of course, being on the same side, just as you saw with the cyclohexanes. Trans being on the opposite sides of the double bond, again, as you saw with the cyclohexanes. These days, as we will expand upon in the next slide, instead of trans, you say E. Instead of cis, you say Z. Now, you're going to have to forgive my American background. I will often say Z instead of Z, but if I say Z, I mean Z, so no issues about it. Now, do note that we only have to worry about whether we have geometric isomers for the but-2-ene, because in order to have a geometric isomer, you have to have different groups on both carbons of the double bond. If we look here, got a hydrogen, a hydrogen, a hydrogen, and an ethyl. It doesn't matter where that ethyl is because it's always going to be relative to a hydrogen. It's going to be on the same side as a hydrogen. It's going to be opposite a hydrogen. Same thing for the 2-methylpropane, 2 methyl groups, 2 hydrogens. This methyl group is going to be across from a hydrogen regardless. This methyl group is going to be across from a hydrogen. So you get geometric isomers when you have 2 different groups on each of the carbons in a double bond, either an E or a Z isomer. Let's talk a little bit more about the isomers. Remember, you only get geometric isomers if you have 2 different groups on each carbon in the carbon-carbon double bond. So what you do is you assign a priority to each of those groups using the same CIP priority. So the first thing we do is we say, well, the higher atomic number is the higher priority. And we'll see some examples of that in a minute, where you just look at the 2 atoms that are bonded to a particular carbon, whichever bonded atoms got the higher atomic number, it's higher priority. If, on the other hand, both atoms that are bonded to the carbon are the same, then we just keep going backwards to see what else is bonded to till we get a difference. And if we have a multiple bond, then that means if it's a double bond, you count atoms twice. If it's a triple bond, you count them thrice. Once you've assigned the priority, if you've got the higher priority on opposite sides of the double bond, then it's E. The higher priority for each carbon is on the same side of the double bond, it is Z. Those words, by the way, E entgegen, Z zusammen. I always think zusammen's much nicer than entgegen, but I prefer E structures to Z structures. I'm just weird. Anyway, so that's the first molecule to look at. What I would suggest you do is once a molecule comes up, you pause the video and you try and assign higher priorities. And I'll pause a little bit just so that you've got some time to pause and come back. So I'm back, I hope you are. So we look at the left-hand carbon. We have hydrogen, we have chlorine. Chlorine, much higher molecular mass, much higher atomic number, than hydrogen. So chlorine 1, hydrogen 2. On the right-hand carbon, same process, bromine or carbon. Bromine, much higher atomic number than carbon, so bromine 1. And the methyl group 2. So we have the 2 higher priorities on the same side of the double bond. That makes it zusammen, or Z. Look at this one. Think about it. I'm back. Look at the left-hand carbon. This left-hand carbon bonds to a methyl group, which is C, or a hydrogen, which is H. C, higher atomic number than H. 1, 2. Now this one gets a little bit more interesting. This carbon, the right-hand carbon, bonds to a carbon and a carbon. So how do we tell the difference? Well, this carbon goes to 3 hydrogens. This carbon goes to a carbon and 2 hydrogens. Because remember, ethyl group, you got the carbon that's bonded here, then another carbon there. So the carbon here beats the hydrogen there. Ethyl 1, methyl 2. What we now see is that the higher priority are on opposite sides of the double bond. This is on the top, this is on the bottom. That makes them an E. Third example. I'm back, hope you are. Carbon versus hydrogen. So the ethyl is the higher priority on the left-hand carbon. Here we've got oxygen or carbon, oxygen higher atomic number than carbon. So the OH is the higher priority. So they're on opposite sides. So that is an E, entgegen. Bit more fun here. Left-hand carbon, carbon goes to an oxygen and to a carbon. Oxygen better than carbon, so therefore the oxygen 1, the acid group 2. Here, methyl carbon, hydrogen, carbon better than hydrogen, so 1, 2. So the 1s are on the same side of the double bond, making it the Zusammen, or Z. This one, and of course here you have to know what isopropyl is. Right hand one goes to carbon, goes to carbon. In the propyl, it goes carbon, carbon, carbon in a nice little 3-carbon chain. In isopropyl, the carbon that's bonded to the carbon then goes to 2 other carbons. So this carbon, the isopropyl, is carbon, carbon, hydrogen. The propyl is just carbon, hydrogen, hydrogen. Isopropyl better than propyl. Over here, chlorine obviously better than hydrogen. And so we have the top priorities on the same side, making it Zusammen. Finally, this one, chlorine better than carbon. Now here you got carbon and carbon. In the ethyl group, the carbon goes to another carbon. On the other hand, here, this carbon goes to 2 other carbons. It's a double bond, so we count it twice. So we have this one here, the carbon that's bonded to the carbon, then bonds to a carbon, hydrogen, hydrogen. Carbon that bonds, this carbon bonds to 2 other carbons with a hydrogen, thus it is the higher priority, making that one E. Hopefully that made sense. Practice it. There will hopefully at some point be practice questions up there on the online quizzing for you to try lots and lots and lots. We will of course be revisiting it time after time after time. Now the next movie is one that some of you might already have seen. It's dealing with the whole sigma versus pi bonds, but it's put here because initially it was an extension video. Now it's a special video that applies to alkenes and alkynes and the bonding therein.